In this example, we investigate the chi-square test for independence, and we are going to look at some data from a survey about animal testing. The chi-square test of independence determines if there is a relationship between two categorical variables in one population. It is called a test of independence because no relationship means independent. If there is a relationship between the two variables in the population, then they are dependent. The null hypothesis states that the two categorical variables are not related in the population. In other words, the variables are independent. The alternative hypothesis says that the two categorical variables are related in the population. In other words, the variables are dependent. To test our hypotheses, we select a random sample from the population and gather data on two categorical variables from each individual. As with all chi-square tests, the expected counts reflect the null hypothesis. So the expected counts assume that everything is equal among the two groups. So we need to determine what we expect to see in a sample if the variables are independent. As before, the chi-square test statistic measures the amount that the observed counts in the sample deviate from the expected counts. Animal testing is a controversial topic that people have strong opinions about. The General Social Survey, conducted annually at the University of Chicago to monitor societal change and study growing complexity of American society, asked 1,152 U.S. adults to react to the statement, "It is right to use animals for medical testing if it might save human lives." Here's a two-way table of their responses. So you can see the columns are separated by gender, so we have sorted males and females who responded to this study. And then the rows are the opinions they expressed. So the opinions range from strongly agree, to neither agree nor disagree, to disagree and strongly disagree. And then we have our column totals here. So we wonder, is there a relationship between opinions about using animals for medical testing and gender? This question tests a claim about the relationship between two categorical variables, gender and opinion about animal testing. So a chi-square test of independence is appropriate to investigate this claim. When we looked at the goodness of fit test, we had some sort of population distribution or expected value of things that were equal to do our comparisons to. So in a test for independence, we don't have a set value to try to compare to like we do in a goodness of fit test. So there's a couple different ways we could state the hypotheses. Here's one way. We could say for the null hypothesis, there is no relationship between gender and opinions about using animals for medical testing for U.S. adults. And the corresponding alternative hypothesis would say there is a relationship between gender and opinions about using animals for medical testing for U.S. adults. Here's another way that we could state the hypotheses. We could say independent if we didn't want to say relationship. So the null hypothesis would say gender and opinions about using animals for medical testing are independent in the population of U.S. adults. And the alternative hypothesis would say gender and opinions about using animals for medical testing are dependent in the population of U.S. adults. So it's your choice if you want to describe it as a relationship or to say independent and dependent. So step 2 is to collect and analyze the data. So to investigate the relationship between gender and opinions about using animals for medical testing, we compare the percentage of males and females who gave each animal testing response. So back in an earlier chapter when we talked about relationships and categorical data, when we were doing introduction to probability, these were conditional percentages or conditional probabilities. So we're going to do our calculations restricting just to the probability or percent of males with certain opinions and the probability or percent of females with certain opinions. So in this situation, because we think that the person's gender makes the difference in their opinions, gender is the explanatory variable, and opinion about using animals for medical testing, the rows of this table, is the response variable. So we compare the distribution of the response variable, opinions about using animals for medical testing, for the groups defined by the explanatory variable, the males and the females. This means that explanatory category totals are the denominator of each fraction. So we're going to do the denominator of the males and the denominator of the females. And so you can see those conditional probability calculations here in the table. So the male values are all divided by 516 total males, and the females are all divided by 636 total females. So we're doing conditional calculations. And then we want to convert those to decimal so that we can do a comparison. So just eyeballing my decimal comparisons, it looks like males are more likely to agree and strongly agree. And it looks like females are more likely to disagree and strongly disagree when we look at these conditional probability differences. So we could call these conditional percentages if we move the decimal point over. I left them in probability form as a proportion. So do the conditional percentages or conditional probabilities in decimal form like I have them indicate a difference in opinions about using animals for medical testing? Well, it seems that males are more likely to strongly agree or to agree, and females are more likely to strongly disagree or to disagree. So we're going to put our data in StatCrunch. You can actually find the data file animal testing for chi-square independence tests. And then for an independence test, our steps are a little bit different. We go stat, tables, contingency, and then we're going to choose with summary. And so we'll follow these steps. So here's my data in StatCrunch. I'm going to go to stat, tables, contingency, and then with summary because these have already counted all the results of the study. And so the columns, I'm going to look at our male and female. You can hold down the command key on a Mac or control and click both, or you can drop and drag both those columns. And then the row labels are the opinions, so you can click row label opinion column. If you see how we've got this laid out, the male counts are in the male column, the female counts are in the female column, and then the labels are in the opinion column. And then we can scroll down and we can say, show us the expected count, and then show us the chi-square test for independence. And then go ahead and hit compute here. So notice there's a little note about the cell format. So the counts that we actually saw in our data are the first value, and then in parentheses are the expected counts. And the expected counts are what we would see if the opinions were divided proportionally between the males and the females. So there's less males in the study, 516, so the expected values for the males are lower for each of these categories, but the proportion is the same. So if we look here, it does look like males were more likely to strongly agree and females were more likely to strongly disagree. We have 5 different answer choices for this survey. So 5 minus 1 is 4. So we have 4 degrees of freedom. That's the DF in our chi-square test. And then StatCrunch calculated the chi-square value for us by subtracting the observed minus the expected for each one of these male and female categories, squaring, dividing by the expected, and then adding everything up. And so that value is 47.54. And that's considered a large chi-square value, so the p-value is very small, less than 0.0001. So we are going to write our conclusion now. So we record the chi-square value, the p-value, the degrees of freedom, and then to state our conclusion, we say we reject the null hypothesis. There is sufficient evidence to conclude that opinions about animal testing for medical research depend on gender. And so this is because we have that small p-value that we're rejecting the null hypothesis. If our p-value came out larger, we would fail to reject the null hypothesis like we have in past examples with 2 proportions and 1 proportion. In the next example, we see how to calculate the expected counts. So in the results in StatCrunch, the expected counts were in the parentheses in the table. So we are going to see how those calculations work out. The values in parentheses in the cells of the two-way table in the previous example are the expected counts. In general, the expected counts for a two-way table may be computed using the row totals, column totals, and the table total. So in the strongly agree row, there are 135 responses out of 1,152 total surveyed. So we take the actual values of the 76 plus 59 and add those up to get the 135. So if there was no difference between male and female opinions, we expect about 135 out of the total 1,152 So that works out to be 0.1172 or 11.72% of each column should be in the strongly agree row. Now, to find the expected counts, we use the fact that there were 516 total males surveyed. And so we multiply 0.1172 by 516 to get the 60.47 expected value. And then similarly, since there are 636 total females surveyed, we multiply 0.1172 by 636 to get the 74.53 expected value. So now we're going to check the calculations for the agree row. So the agree row total, if we come back to the first page of this example, was 270 males and 247 females. So we add up the total who agreed and get 517. And then we say, okay, if there was no difference in gender opinions about animal research, we would expect 517 out of 1,152, or 0.4488 of each column in the agree row. So to find the male expected values, we take 0.4488 times 516, and we get 231.57. And then to find the female expected value, we take 0.4488 and multiply that by 636, and we get 285.43. These values are an exact match for our StatCrunch results for the agree row. So if you wanted to continue the calculations, you would go through the counting up of each row total and dividing by the total and then multiplying by the totals for each column. And that's how the neither agree nor disagree expected values in parentheses came about, and the same for the disagree and strongly disagree expected values in parentheses. We're going to rely on StatCrunch. We'll be good to ourselves so we don't have to check this every time we do a chi-square test for independence. We will let StatCrunch do this math for us.